Okay, everyone, on to learning target number 4. We're going to talk about special relativity and general relativity. Okay. First thing I want us to note, though, is we have this entire electromagnetic spectrum, and our eyes are only capable of perceiving such a small portion of that. We have radio waves and infrared rays, we have gamma and radio, we talked about radio x-rays, we have so many different electromagnetic waves. And so what I want you to realize is that what we're capable of viewing is only a fraction of the story, that so much more can be going on in the night sky. Like, this is how we view it, but then if we, compile all the different types of electromagnetic waves, there's a lot more going on there. So, these electromagnetic waves, it was first thought through by Maxwell that light traveled as an electromagnetic wave. And so then the math came along to support that idea. And light, which is part of this electromagnetic spectrum, was a key component to Einstein's special and general relativity. Okay, so first thing to note, something you've seen probably before, the speed of any electromagnetic wave through space is about 2.99 times by 10 to the 8th meters per second. We'll talk about that more in a little bit. All right, so relativity. What is relativity? Two types here. We have special relativity and general relativity. Special relativity, which is concerned with objects and observers moving at a constant velocity. Okay, so this is when we do not have acceleration happening, which we typically see in the presence of a gravitational field or object, right? And so it is constant velocity components. And then general relativity is trying to take the information we gain from special relativity and apply it to accelerated frames of reference, okay, both of the observer as well as the object. So the main idea is that we can have different observers moving in different reference frames, which means that they can be observing the same phenomenon but seeing it differently. And so from this idea, we had this classical relativity first introduced by Galileo and Newton. We've spent a lot of this year talking about Newtonian physics, establishing origins, working through that frame of reference, and that'd be this classical relativity. And then Einstein developed the modern theory of relativity. Okay, Einstein based this idea of special relativity on two postulates. Okay, and the first one is that all the laws of physics are the same in all inertial reference frames. Okay. Inertial. Remember Newton's first law of inertia? An object in motion will remain in motion, an object at rest will remain at rest unless acted upon by an outside or an unbalanced force. That we will have these laws, these Newtonian laws of physics, are going to be all the same in inertial reference frames. And then the speed of light in a vacuum is a constant. So it independent of the motion of the light source. It doesn't matter how the light source is moving, we're still traveling at that speed, the 2.99 times by 10 to the 8th meters per second, in a vacuum. Okay. All right, first postulate here. Let's go into detail about this. So all the laws of nature are the same in all uniformly moving reference frames. Okay? So meaning that we have uniform motion, constant velocity. Now this is interesting because we don't have any experiment that can detect if we are in a uniform motion or not. Okay, we can determine if we're in a uniform reference frame, but uniform motion, constant velocity. Okay, think of it like this. If you were in the back of a car and the windows were covered and you wake up, you wouldn't know if you were moving or not. Because you could be moving at a constant velocity or you might be stationary. And so we don't have an experiment of making that detection. We're not able to determine if we have uniform motion. Okay? So, finding an inertial reference frame first. The modern definition of inertial reference frame is one in which Newton's first law holds. We talked about Newton's first law. Now we can observe what's happening to particles in a reference frame and then make that determination of if it's an inertial reference frame. If we're moving at a constant velocity, then the reference frame is an inertial reference frame. And then all the other laws should apply if that is the case, if we're in that inertial reference frame. All right, let's look at an example. We have two inertial reference frames here. Okay, we're going to have Ted's reference frame and Alice's reference frame. And Ted is going to be moving with a constant velocity in the x direction, and Alice is going to be stationary. So we have two inertial reference frames in the x direction. What we have going on here is, from Ted's point of view, from his reference frame, he tosses a ball in the air, it goes up, and then it just comes straight back down and he catches it. But remember, he was moving at a constant velocity in the x direction this entire time. So if we're viewing that motion of him moving through the x direction at that constant velocity, what we view is a parabolic path taken by the ball, not the ball just going up and down if we're this outside observer in a different inertial reference frame. So different reference frames can have different observations. But in both situations, Newtonian laws held. That we had all those Newton's laws held true for both Ted and Alice and what they observed. So the principle of Galilean relativity is the idea that the laws of motion should be the same for all inertial reference frames. Okay, take a moment and describe what was observed of the motion of the ball by Ted and then by Alice. Okay, so hit pause, give me a couple sentences, and then come back to it. Okay, so there's some things that they agreed upon. They agreed that the ball's acceleration is downward with a magnitude of g, 9.8, 1 meters per second squared. Both agreed that the ball's horizontal acceleration was 0 because the velocity in the x direction was constant, so that would be an acceleration of 0. Both agreed that the only force acting on the ball is the force of gravity once it left his hand. Nothing else was acting on it. And that Newton's second law is obeyed. Okay, so that's the first postulate, inertial reference frames. The second one, that the speed of light is constant, it has that magnitude 2.99 times by 10 to the 8th meters per second. in a vacuum regardless of the motion of the source. Okay? So the speed never changes, but the frequency of light that reaches you, that might change. Okay? So if the frequencies are changing and the speed is remaining the same, then what other component of light is changing? Remember this equation where the speed of a wave, whether that's sound wave, light wave, whatever, is equal to frequency multiplied by wavelength. Now I put the letter C because that's typically the variable we use to represent the speed of light. So the speed of light would equal the frequency of that light wave multiplied by the wavelength. So if this is changing and this is remaining constant, in order for that to remain constant, the wavelength must also be changing, and they're inversely proportional. As frequency becomes larger, wavelength becomes smaller, and as wavelength becomes smaller or larger, frequency becomes smaller. Okay? Inversely proportional, and that interaction of being inversely proportional is what keeps us constant. So his equations show that the speed of light is constant and that it's independent of motion of the source. Okay, so here's an example of this, and it's pretty amazing to think through. So we have two inertial reference frames again. Alice is traveling at a constant velocity of 0. Ted's traveling with a constant velocity in the x direction. Ted's going to turn on the flashlight. Okay? This is going to interact very differently than if you threw a ball. Because if Ted were to throw a ball, Alice would perceive that ball going at a speed of it being thrown plus the speed of the cart. But it is not what she detects when a flashlight is turned on. She observes the speed of light to be 2.99 times by 10 to the 8th meters per second. And then the amazing thing is that Ted does too. Both of them, in different inertial reference frames, observe light being that constant 2.99 times by 10 to the 8th meters per second, not the c, the speed of light, plus the speed of the cart. Now, experiments showed that Maxwell's theory was correct, and that the speed of light in a vacuum is always that 2.99 times by 10 to the 8th meters per second. We can see a shift in that frequency, right? Like if it's going to be traveling at that speed and light's being produced, they can stack on top of themselves, just like in the Doppler effect, and we can see a blue shift if something's traveling towards us, but that speed is constant. All right, so Einstein's working with this idea, and he wants to explain this situation. Like, why is it that when Alice observes the light, she sees it going 2.99 times by 10 to the 8th meters per second instead of that speed plus this speed? Okay? So he suspected that the speed of light was the same in all reference frames. And then we had to work out the implications of how that would even be possible. Oh, right there. So that must mean that a time component has to come into play. And so this describes time and its effect in motion and space, and this space-time fabric and continuum of the universe. Okay, let's talk about space-time. Oh, where are we at time-wise? Okay, we're gonna continue on to the next video with space-time.